So this will be available on the YouTube channel itself. Okay, so here is something which are you able to see this, or should I share it?
You should share this.
I should share it.
Yes.
Okay. Okay, now you should be able to see. Yes. Are you able to see?
Yes.
Okay. So let's start off. This is from a different book, not from the book that is recommended, I think. It's a book that I got it as a gift based on something, but the explanation in this book is too good. So I took from this book to explain. So here is something which will help you to understand more. Okay, but the same examples, right? Same examples that I did, XR and all those things. We talked about this biological neuron, right? And nucleus, cell body, axon, and the synapses. Through the synapses, again they are connected to dendrites, to other cell body, to the dendrites of the cell, and that's how the neural network gets the communication between the neurons happen. Now this is the equivalent of the biological versus the artificial neural network. Biological is soma, artificial we call it as node. Dendrites the input, axon is the output, synapse is the weight, slow, fast, based on what happens. And many neurons are there, few neurons, a dozen to 100 thousands are there in our cell body. So that's how they are communicating and letting our brain know, and that's the reason that we have a reaction to that one. Now this is the representation to it. Okay, the inputs x1 to xn, and each of them has the weights. They go through a processing entity through which, wherein the processing unit is called as the sigma I to the sigma, that means sigma of I to n, where xi wi, and they go through a neuron. This is the neuron, the circle is the neuron, and that comes out as an output depending upon how you want it. Is a single output or multiple neurons, multiple output, depending upon how within the neuron I can actually have multiple outputs as such to give me whichever outputs that need to be outputted. Okay, and so this composed of processing elements. So this neurons, the basic P unit is the neuron. The number of neurons are then organized into a network. Neurons can be organized, and these various network patterns are referred as topologies. And the PEs, the basic processing entities of ANN are artificial neurons. So the output can be final result, 1 being yes, 0 being no, but these are all if it is a binary output, but depending upon what kind of classification that you are doing, the neurons, the final layer can be put upon properly. So this input layer, hidden layer, and the output layer, if you look at it, this is how it is put. All the processing unit, they are all connected, fully connected to other processing entities within the hidden layer, and these processing units go through neurons. Okay, they go through neurons to another processing unit, finally the output layer. And then network structure, I think this is just the best is to see an example. The connection weights, the weights express the relative strength of the input data that fed into the input processing unit. And as I told you earlier, that weights makes it more relevant in terms of whether that particular input is good enough to give an output. Okay, that weight determines and the input that is taken, they both get through the processing unit, either it is a summer or a multiplier or whichever kind of a entity that processing unit happens to be. Based on that, the output actually is determined. Now if you look at it, this is the summation function. Now if you look at the summation function x1 w1 processing unit, and this is how the output is actually the single neuron output. And if you look at it, the y1, if you look at the second neuron, second diagram over here, which is this one, I'm not able to write it here, wait. All the entities, where are they? Pointer function, pen. Okay, so this one, this y1 is within this processing unit. Okay, this processing unit, this w1 w2 all these things comes in, and that's the reason this y1 function. Similarly the y2 and the y3. Okay, I don't need to explain, it is self-explanatory. I think we have done it. I'm just recapping it, so don't take it, okay, well, you might not even want to write it, but because I'm going to share it anyway. Now the transformation function, this is one thing which we kind of I kind of explained it, wherein the alpha beta is equal to 1 by the sigmoid function, beta is equal to 1 by 1 plus e to the power of minus alpha or yt, and this is the normalized function, right? So this is where the summation function go through the neuron, where the sigmoid function, a logical activation function, which is the sigmoid function, through which the output actually gets normalized. And this minus y is the actual the output that comes out. Based on that, the transformation function works as such. So you can look at this later. And if you look at this part one, which we kind of let's look at now, knowing those function, let's look at how this processing unit and the y which actually comes out, and how the neuron, the output of this neuron, this goes through another neuron here, right? Whatever comes over here, that this is this yt, and that yt is basically is this function. Now what is the value of y here? Is this total processing unit function, which is x1 into w1 plus x2 into w2 plus x3 into w3, going through this processing unit, gives me 2.6, and that 2.6 is the input to this neuron, which gives me the final, where yt is equal to 1 by 1 plus e to the power of minus y. What is this y? This y is this, and this is this. That I put it as part of this equation to get as 0.93. So this is the output of the function that actually happens through the processing unit. So this is how one of the other, maybe I did not teach this, but this is also part of that neuron network. Okay, don't get confused. They're all within the part of the neural network architecture. Okay, now let's look at this R function truth table. Now this is where you might wonder, sir, when we did it, what was our equation? When we did the R equation, what was our this thing? Equation was y is equal to x plus 0.5, isn't it? The R function. This is the R function, right? The truth table for an R truth table. Okay, yeah. So then we put it as minus x plus y is greater than or equal to 0.5, right? Then what was our weights? Our weights was minus 1 plus 1, right? Minus 1 into x plus 1 into y is greater than or equal to 0.5. But we kind of assume that it is minus 1, isn't it? Is it the right correct w1 value or w2 value for this particular equation for the R table? Maybe not. Maybe we might get a proper answer to it as such. What should be the w1 and w2 value if it goes through a neuron, and if it goes through some iterations, what should be the delta value that needs to be changed such that we get a very near to the weights of this particular equation, such that it is true for all purpose, all inputs, not all purpose, for all inputs it should be true. Now what should be that w1 and w2? How do we determine? Based on this particular error correction that happens is the error correction which needs to go through each of these w1, that error correction that needs to happen is equal to w1 plus r into delta into xi. This is very important equation that you need to know is what is that error correction that I need to have, that I need to have that needs to go through this is that w1 plus r times delta times xi. What is this delta I? Is this delta is the w change in wi that needs to happen, and multiplied by xi. Again, that xi is the same input that needs to go in. So this particular equation is very important, where the new w is equal to w1 plus r times learning rate times the delta change into xi. So this equation is very important. This equation is very important. Sorry, what do we do? Okay. So this equation is very important. The change is equal to w1, the original w1 plus learning rate times the delta, where delta is equal to the change that needs to happen times the x1. This change in w1 or delta is, let's look at this XR function. When it started with 0 0 and the output that comes out is equal to 0, this is the original truth table, right? x1 x2 0 0, the output is 0 0 1 1 1 0 1 1 1 1 1 1. So this is the actual output. But let's say we start with an initial value of 0.1 and 0.3, where w1 is 0.3 and w2 is 0.3. But if you multiply and the expected output through this neuron, and the delta is the change that needs to occur, where delta is equal to z minus y, the desired output minus the actual output that comes from the neuron. What is the desired output here? Z. What is the actual output that came? Let's look at it here. When 0.1 and 0.3 was used, the actual output was 0 and the original output was 0. When you run through this whole equation, this is what it came. So the delta is 0, right? 0 minus 0 is 0, and the original value that was given is 0.1 and 0.3. Now how did I get this 0.1 and 0.1? If you put all this formula inside in this one, this new w1 is same and w2 will be the same, 0.1 and 0.1. I will put this 0.1 and 0.3 as this one as the values over here, and again I will do the same equation. Now I get 0.1 and 0.5. Now I will put this 0.1 and 0.5 as the next input to this one. Again I will do this continuously for maybe n epochs. When I run this code, I have this Python code somewhere, but I'm not able to find it. In the fourth iteration, they come as 0.7 and 0.7. They will come as 0.7 and 0.7, so that the final value of W1 that for all kinds of input, if I use 0.7, W2 is 0.7, the output will be exactly the same as this, the expected output of 0 for this OR table, 0 1 1 1 1. I don't have the actual calculation here, but I had a Python code, but I am not able to find out because this is another machine, so I don't know where exactly that code has gone, but maybe next time I will show it to you. So that's how this particular equation will come in. I hope you understood. So the neuron for the OR table is done similarly like this, but if you are interested in writing a code like this, you can take it, you can work it on this Python code, okay, and you can write an iteration of 4 or 5 and you will get the answer as 0.7 and 0.7. So that means you start with x1 with x2 and XOR with this one, and you write an equation for w1 into x1 plus x2, and then you have this equation. Then you will, if you run this in a for loop for 4 times, you will get the answer. So that's how the program is written, the Python program is written. And similarly for NAND and truth table or an XOR truth table, all of them are similar. Similarly, they will be done. You write just for AND and OR. XOR is 2 equations, so you will need a different kind of a program for that to run properly. I hope you have understood this part. Now coming to the reason I told all this is for this particular equation. When I did this truth table, remember the original was where I'll just run this once again, and pointer pen. Okay, the original equation was that the change in W1 is equal to learning rate times, I put it as out A.
Sorry, not sharing screen.
Oh, sorry. 1 second. Thanks for reminding. I forgot to. I closed that one. Right. 1 second. Okay, this one. You're able to see now?
Yes, sir, we can see it.
Okay, sorry. This particular thing, you remember I did it in the class, right? But there was one last thing that I kind of messed it up, was that I gave R times out A times neuron of 1. I wrote something like this, and out A was half, right? And this was also half, and this whole thing was half to the power of 3, remember? And this one was what was wrong. Okay, this one is supposed to be learning rate half times 50 times half to the power of 3. Why? Because I remember just now we did what did we do? The change in was W1 plus learning rate times delta times xi. Remember, delta times xi. This xi was what was missing. This was supposed to be xi, but I told out here. So the xi, what was the xi over here? Was 50, isn't it? So this change in W1 was supposed to be half times 50 times half to the power of 3. So this was supposed to be the answer, okay, not the one which was something else which came. So that was the reason I had to teach that part. Remember that this is the equation that you need to remember. What is the delta that I need to change? Is W1 plus learning rate times delta into the input for the one which we are working on. So that was the reason I had to do this, to give it you 50. So this is the answer that's supposed to come. Please change it in your notes, okay? So this was the mistake I did in the class. So this is the change I wanted to do. How did I come to arrive this? Because of this equation. So please note this equation. Anyway, I'm going to share this PPTs and put it there. So I hope this makes some clarification as to why this answer is, okay? So now I'll get on to convolution network. So this was what I wanted to share with you. Now let me share another window, which is this Jamboree. Convolution network. Now you remember this whole thing, why convolution network and neural network, why we call this, and why this let's start with one thing. Let me put this okay, so there is an image. Okay, which is, let's say, 24 by 24. Okay, 24 by 24 image. Which needs to be detected. Some image is there, okay, some people are standing here, okay, something like this, and somebody is here, okay, and some distant people are standing here, okay, and there is a railing here, which is railing, and this is a seashore, okay, and maybe there is some kind of moon is standing over there, and distantly there is a ship. That is a ship, don't know, okay. Let's say there is something like this, and it's a 24 by 24 pixel image. Now if you want to find the edge detections, that means you want to find out whether there are some people standing, or somebody else is standing, or if there is some kind of something floating on the picture, on the image, something is floating. You need some kind of some techniques to identify that there are people standing and there is a railing standing. If there is a people, if the railing actually gets identified as people, or people get identified as railing, we don't know what exactly is that picture supposed to be. Because that's where we need to identify that that picture has these kind of objects sitting in there. Now how do I identify, how do I make this particular edges to be detected? Maybe right now I am just saying horizontal and vertical detection of an image. Let's say there are some cross sectional or 70 degree or 45 degree, there are some things, some other images there, but I need some kind of something that I need to identify such that it some kind of filter that I need to put on this particular image such that it says that okay, you identified this many this kind of edge the edges are there in this picture, and there are some horizontal edges are there in this picture, but how do I filter them? What are the ways? But if I take this 24 by 24, that itself is 476, right? And think of it, 476 inputs, and just now I took only 24 by 24, right? X1 through X576, right? 576 X0 to X575, right? And they going through some neurons. Silence yourself, please. Who is it? Thank you. Now these neurons, if at all every neuron has a fully connected neurons. Let's say every neuron is going, every input is going through every neuron, then it is called a fully connected neuron, right? X, this is the input pixel, and they going through sort of some hidden layers. Let's say there are so many hidden layers, okay, and they might get decreased or they might increase, we don't know what is the possibility. And there are some outputs, and this is the output layer saying that I identified some men, some female, and some dog and some sheep. I don't know what kind of output that might come out of here that gives a weightage to find out what they are, right? Now think about it, just with 24 by 24 bar pixels with so many inputs and so many bias, so many inputs of information that goes through that, and moreover every input, when there is an input, there is always the bias also, right? Some kind of weight which gives a boost to whether to use that input or not, right? The bias is also important. It's just not the x1, right? It also goes through what is the weightage and what is the bias, what is the threshold through which it's supposed to go through. So think about it, if at all I have so many inputs, so many pixels of inputs, and so many neurons that I need to give, if at all I need to go through fully connected, I will have to have a big, massive calculative data center to do it, just for 24 by 24. Now let's say there is the image which is 5000 by 5000, okay, almost 25 million pixels. Think about how large the neuron would be. It's unimaginable as to how many inputs that it has to have, going through every neuron, doing processing of it, and once forward propagation, then again everything back propagation. It would be enormous, isn't it? So how do we solve this part of where we need to reduce this such that it is done in a very lesser number of it, but still able to capture everything, right? So now let's look at what pen I have. So let's look at the blue pen. Now let's see if this is where we need to, now for the edge detection, now let's take again the same thing. I have a image which has some kind of inputs, right? Right, and I need to identify some edges, vertical edges. Now for vertical edges I might take something like this, wherein it's a 3 by 3 filter, a 3 by 3 filter, okay, which might have 1 1 1 0 0 0 minus 1 minus 1 minus 1, where 1 leads to be some kind of information is there, where 0, if you understand pixel, this gives black, more gray or black, or more negative the number, more darker it is, and more bright, some number is bright, okay, more darker. If this filter is used such on this particular pixel, okay, on this particular image, which is, let's say I take this image now, let me take a proper this thing, okay. Now if I take this, a 6 by 6, one, 2, 3, 4, 5 and 6, 1, 2, 3, 4, 5 and 6. Now let me take an image which has, let's say 3 0 1, okay, 2 7 4 1 5 8 9 3 1 2 7 2 5 and 3 0 1 3 1 7 8, and let's say 4 2 1 6 2 8 and 2 4 5 2 3 9. Okay, these are the ones. Now if I want to apply this filter, apply the filter on top of this, it is a 3 by 3 filter, and this is a 6 by 6 filter. This is a 6 by 6 image, okay, pixel, and this is a 3 by 3 filter. If I want to apply it, now what I will do is I will apply this filter first on top of this, okay. That means this would be 1 1 1 0 0 0 minus 1 minus 1 and minus 1. Now once I convolute this symbol of multiplication is called as convolution, okay. If I convolve on this, I will get a 4 by 4 image or convoluted image. I wouldn't say image, it's a convoluted image. Why? Because it might not be the original image, it is a modified, because I'm applying the filter on top of it. Now whatever image that the numbers that might come on this might be different, right? So now how do I get this number? What I will do is 3, how does this number get filled up is 3 times 1 plus 1 time 1 plus 2 times 1 plus everything on the middle is all 0 plus minus 1 into 1 plus 8 into minus 1 plus 2 into minus 1. If I add all of them, I should be getting something like minus 4. If I now what I will do, I will stride a little bit. Now what I will do, I will go to the next one by sliding to the next pixel. Now I will use the same filter, but now I will apply on this part of it. This part of it. This part of it. Now I will apply the same thing. Now I will do what I will do is I will apply 1 1 1 0 0 0 minus 1 minus 1 minus 1, and I will do the same math, same kind of math. Then I should be getting minus 4. Okay, and now I will again stride to the next one. This one, sorry, this one. I will stride to this one, and I will stride then to the next one. That means if I use a 6 by 6 on a 6 by 6 image pixel, when I use a 3 by 3 filter, I will get a 4 by 4 image, convoluted image. And what would be the numbers that would come over here? It would be 0 and 8. Now what I will do is I will slide, and now I will apply the same 3 by 3 bar on this part now. Maybe I should use a different ink now. Okay, wait. Now I will stride down to this one, and again I will do 1 2 3 and again 4. I will do something like this, and I should be able to, I would do the same filter. I am applying this 1 1 0 0 minus 1, and I will get something like minus 10 minus 2 2 3. Then I would do the same thing again, slide, one more slide. I should be applying on this one, right? I should be applying something on this one, then on this one, and again slide it. Now the whole thing will be converted to something like 0 minus 2 minus 4 minus 7 minus 3 minus 2 minus 3 and minus 16. So an image of 6 by 6, when I apply the filter something like 1 1 0 0, is this the only way that needs to, is this standard? Need not, this need not be. Can somebody please mute yourself? Thank you. So what we got, a 6 by 6 on top of 3 by 3 filter, we got a 4 by 4 image. Okay, now I can also, this is vertical edges can be identified. Vertical edges can be identified by using 1 1 0. Now you might think, sir, how do I get a horizontal? So the horizontal image would be something like this. You can apply the same thing, wherein the horizontal images can be something like this, where 1 1 1 0 0 0 minus 1 minus 1 minus 1 minus 1. So is this the only way? Maybe not. Maybe there might be different ways. So this filter is called as, this filter where 1 1 0 is called as Schar filter. Schar. It's called as I think one of them is Sobel filter, and other one, this one is another This is a vertical edge detection, and this is a horizontal edge detection. There is another kind of thing. Even there are different kinds of filters were used by different people. So the next one would be something similar to like this, where um, where there were other filters that were used by different people when they were working with it. They name their own filters with their names. So this is another one, which is 3 10 3 0 0 0 minus 3 minus 10 minus 3, and this is called as Schar filter. Okay, and there was another kind of filter which was also used. Again, I'm only talking about 3x3 filters. Can we have different kinds of filters? Absolutely. But how do you use, what is the weight, what are those numbers that would come up, is something which is static here. These filters are static in nature. So the one which another guy gave it is 1 2 1 0 0 0 minus 1 minus 2 minus 1, and this is called as Sobel filter. Okay, now using this kind of filters gets you to one particular convoluted image information. Okay, something from a bigger image to a smaller image. You should understand why we are doing. The reason we are doing is because we have lots of inputs, because each box is an input. Each box gives you an input of a pixel information that needs to go through neuron, and that each input has some weight and bias on which then it goes through a neuron. That neuron has to process everything, passing that information, whatever comes through that neuron goes to another neuron. So if it is just by 24 by 24, it gives a bigger number. If you think of an actual color picture, or a picture which is 1 megabyte pixel, that itself is a bigger one. Think about it, how many neurons and inputs that we need. Okay, so for that reason we are reducing that inputs to a smaller size, such that it is properly sent through neurons to get a proper output. So now let's see how, if now, I'm always saying now, so don't tell me that this sir is now sir. Okay, now here it is. Now if you look at it, the 6x6 neuron, let's take 6x6 image, right? We got 6x6, sorry, this itself is little, let me take to the another page, sorry. Now here is 6x6, 1 2 3 4 5 6, 1 2 3 4 5 and 6. So this is a 6x6 convoluted through a 3x3, which you got a 4x4. Three by three two-way filter. So if you talk about this is n h height times n w and this is filter is equal to 3 by 3, and you got a output of 4 by 4. Now if you look at it, you got 4, and how much of it did you stride? You strided only one by one, right? First you had this, then you moved, this is 1, and then you moved only one pixel, right? You moved only one pixel, so you strided only one, right? You slided or strided only one. Now if you look at it, this the output that you would get, the output filter, the output by output, or number of pixel by number of pixel, is equal to n, should I talk right now? N minus f plus 1 into n minus f plus 1, right? That's what you got. What is n here? 6 minus 3 plus 1 into 6 minus 3 plus 1, which is equal to 3 plus 1 into 3 plus 1, which is 4 by 4. That's what you got. How did you get this? How it's a two-dimensional. This is again 2D which I am talking about. Two-dimensional pixel, image pixel, and if you took grayscale, you can think of it as a grayscale, a black and white 6 by 6 pixel. When you go through a filter of 3 by 3, you got a 4 by 4. That means if you are using only if you use this kind of a setup, right? Now let me take, because let me copy this. Add an image. Laser, no laser. Okay, so now you understood how I am actually writing, right? So if it is this, now if I take 8 by 8, let's say take 8 by 8. If it is an 8 by 8 pixel convoluted with a 3 by 3, what is the output? You tell me now. It is 8 by 8 pixel and convoluted with a 3 by 3 filter. What is the output? It would be a 6 by 6, right? It would be a 6 by 6 convoluted image. Wow. 8 minus 3 plus 1, right, which is equal to 5 plus 1, which is equal to 6. So it will give you a 6 by 6. Now you might ask me, sir, when I'm doing this 3 by 3 filter, what's happening is that this column and this column are not being utilized properly. This column might be, but at least this particular column is not being utilized properly. This particular thing is not being utilized properly, right? So we have something like that. This particular, how do I utilize this particular column also? There might be important information. There might be an eye sitting over here, or there might be a bird sitting over here, or there might be a man standing over here at an edge, or there might be something over here. But if you look at it, if I am striding this particular filter once here and it is actually going over here, the ones which are being utilized mostly are the ones which are in this portion, right? This portion, these pixels are being utilized n number of times when I am doing this, applying the filter on top of it. But for this particular column, I might not be using that much. So how do I make it happen? And moreover, if I come to this particular also, it's only used only once. This also used only once. This also used only once. So how do I make use of this whole picture properly is when I will be able to use when I pad it properly. When I pad that information properly, now if I look at it, I have 1, 2, 3, 4, 5 and 6. 1, 2, 3, 4, 5 and 6. Now if I pad and another one more round, over here, that means I am padding one here, right? One here, right? If I pad an extra 1 pixel around that image, that means this was the original image, right? Which was the original image? This was the original image. This was the original image. But I padded one extra over here and one extra over here. That means I padded 2, right? Padding is equal to 2. If I padded 2, okay, then now how much did it come to? It started with 6. Now I padded 2 of them. 1, 2, 3, 4, 5, 6, 7, 8. So now it became a 8 by 8 pixel. Now if I apply 3 by 3 on top of 3 by 3 filter on top of that, now I'll get 6 by 6. Now that means the original image that started off with 6 by 6, if I pad with 2 more pixels, I will keep the original image. What does it mean now? And how much I'm striding still? Now, let's talk about striding later. Now n plus 2p minus f plus 1, right? And this would be one of them. nh is equal to nw would also be n plus 2p minus f plus 1. Now how much is it? It started with 6, right? 6. How much did I pad? 2. I padded 1 this side, 1 that side. So it is 2 minus 3 plus 1, which is equal to 8 minus 3, which is 5. 5 plus 1 is 6. This also will be 6. So I would get a 6 by 6 filter. And this is called as valid and same. A valid is the one, a valid convolution is something which turns out to be lesser than the original image. That means the one which started with 6 by 6 convoluted with 3 by 3, we got a 4 by 4. This is called as a valid. And one which is same is the one which after padding gives me the same. It started with 6 by 6 to give me a 6 by 6. This is called as same convoluted function. Convoluted function. So to get a same function, to get a same convoluted image on the function which we started was with n plus 2p is 2p minus fp plus 1 is equal to n, right? That means whatever we started with, applying the filter, if we want to get the same convoluted image with n times m, what should be the number of padding that should be? So that means if I apply the math now, these two will be gone. So that means this will be 2p is equal to f minus 1 by f minus 1, which is p is equal to f minus 1 by 2. Now if I want to have, let's say the filter is filter is 3 by 3. All I need to apply, how much is the padding that I need to get based on what it's supposed to give is 3 minus 1 divided by 2, which would be 1. So that means the padding should be done with a 1 padding should be done for if I need to get the same convolution. That means if I started with the 6 by 6, okay, with the 6 by 6 image convoluted with 3 by 3 filter, if I want to get a 6 by 6, then I need to pad 1 extra, then only I will get a 6 by 6 image. I hope I made sense today as to till the padding part of it. Okay, tomorrow we will look at strided convolution, and after that we will look at color images as to how color images will work with. Okay, I hope I made sense. Are there any doubts? I'll stop it now because till this point I think it was I hope it made sense to a lot of people.